Okay, chapter 18 is about thermodynamics. It's quite a word. And you can think about it, thermo means heat and dynamics means like motion and movement, and thermodynamics is the study of heat and work through processes. Chemical thermodynamics is from a chemist's perspective. But what you'll find in this chapter is that when we start to look at heat and work, a whole vista of interesting consequences open up. And so thermodynamics is really going to be a lot more of a broad and an interesting topic than just calculating how much heat is released in a reaction, for example. And in particular, it's going to inform us about the spontaneity of processes. And to understand what we mean by chemical spontaneity, let's look at a couple of processes. So here we have a chemical reaction. We'll say that this isn't an equilibrium. Okay. Au2O3 solid plus 3H2 gas. There we are. This is a chemical equation. It's balanced. I could find out what's the enthalpy of reaction for this equation. I could calculate the grams of product that you might expect based on amounts of reactants. There's only one problem with this reaction, and that's that it doesn't actually occur in nature. This is gold plus water turning into some oxide. Lots of metals will do that. Iron turns into rust, copper turns into copper oxide, the greenish color of the Statue of Liberty, for example. Lots of metals will do this, but gold is not one of them. If you find an ancient shipwreck at the bottom of the sea, if you're fortunate, you may find a stash of ancient gold coins, and they will still be shiny because they are still AU solid. All those hundreds of years of even salty water is not enough to corrode them. This process simply doesn't happen in nature unless it is driven by other extraordinary circumstances. So why is that? Well, we'll call this a non-spontaneous reaction. And part of chapter 18 will be exploring the hows and the whys of identifying reactions that are non-spontaneous. Now, I want to contrast this with another reaction, and that is the reaction of one allotrope of carbon, diamond, turning into graphite. So graphite, oops, that's a C, not an opening parenthesis. Okay, so carbon graphite and carbon in the form of a diamond, they have the exact same elemental composition. They're just carbon atoms. And the way that they are bound together is very different. The diamond is in that tetrahedral covalent network solid. That's what gives it its optical properties, makes it transparent and brilliant, and what gives it its strength. Carbon graphite is carbons that are bonded in flat sheets, and that's really important to its interesting electrical properties and its usefulness in pencils for writing and such. So this is a chemical reaction that could occur, and in fact, by the end of chapter 18, you'll be able to show why this reaction is chemically spontaneous. Now, that doesn't mean that your diamond jewelry is about to turn into graphite. We don't observe this reaction in nature either, but technically it's just because this is a very, very slow reaction. So this reaction is so incredibly slow that it would take longer than the 13.5 billion year lifetime of the universe for a diamond to turn into a graphite. So for all intents and purposes, this reaction will never occur. And yet, from a perspective of chemical thermodynamics, it is a spontaneous reaction. It's simply very, very slow. This one also will not occur, but it's not a matter of being slow. We could wait for the lifetime of the universe. We could wait for the lifetime of the universe times the lifetime of the universe times a Google and square that. And it still would not occur because chemically non-spontaneous processes simply never occur. Okay, anyway, so let's start to talk about thermodynamics and how the study of heat could possibly provide insight into these sorts of questions. Well, there are three laws of chemical thermodynamics. And the first law says that the change in the total energy for the universe for any process is equal to 0. In other words, energy cannot be spontaneously created from nowhere, and energy cannot be eliminated or destroyed into nothingness. Certainly we can generate heat by burning fuel, but that energy was always there already in the first place, in the form of chemical potential energy. We could consume a lot of energy, say by powering our car or by heating our home. That energy doesn't disappear into nothingness. It is dissipated as heat and radiates out into the rest of the universe eventually in the form of infrared radiation. And so if you're studying processes, the first law of thermodynamics says you can rely on there being a net equal energy at the end of your process as at the beginning of the process. And you might need to get a little bit tricky and say, well, in nuclear reactions, there is some energy that is released that was originally stored in this kind of unique sort of potential energy that's represented by Einstein's famous equation E equals mc squared. But even those nuclear reactions which extract an extraordinary amount of energy by converting mass into energy, well, it didn't come from nowhere. It was there all along in this form. Okay, and I guess I do want to say that all three of these laws of thermodynamics, well, who's the lawmaker? Why are these laws? What we really mean is that in all of the history of all of the scientific inquiry of all humankind, we've simply never observed anything that violates these three laws. So what we should really say is the three really reliable observations about thermodynamics. But that's obviously a not very catchy way to describe them, so we call them laws of thermodynamics. Okay. The second law of thermodynamics has to do with entropy. And I'll write the law up here right now, and it's one that perhaps you've heard before, but it's not going to make perfect sense to you until we do some definition. But anyway, we'll put this on here. The delta S for the universe for any process is going to be greater than or equal to 0. S here is a new quantity. It is called entropy. All right, and you may have heard of entropy before. It's actually kind of hard to describe. Some people will call it a measure of the amount of chaos in a system. I think that's a little bit poetic and perhaps overly dramatic. Other people will describe it as the amount of disorder in a system. And those are ultimately kind of intuitive but not mathematically precise definitions. And so one of the things we're going to do is talk about entropy in terms of mathematically rigorous and precise definitions. The reality is that entropy was first defined as physicists were investigating the efficiency of different refrigeration cycles. So the way a refrigerator works is it'll take a fluid, a refrigerant, and it will compress it and on the coil outside of your refrigerator, and that will release a bunch of heat into the room, and then it will expand that gas inside the refrigerator, and that will cool it down and allow it to take heat away from all of your food products in the fridge, and then it will compress it on the outside, and it's this cycle. The gas gets compressed and expanded, and there's a heat exchange after each of those steps. And so physicists were studying all of the properties of the gas as it was compressed, as it was expanded, as heat flowed into and out of the gas, and they found that it was convenient to calculate this integral. I'll make my cue a little better. There we go. The integral of the change in heat over temperature. And I don't want to get into it too much, but they found that they were calculating this integral over and over again, and furthermore, it seems to be a state function. And that meant that it doesn't matter the details of your refrigeration cycle, whether you compress it a lot or a little, whether it exchanges a lot of heat or a little bit of heat. It doesn't matter as long as you do a complete cycle, and I'll represent that with like a little cycle right there. As long as you do a complete cycle in your refrigerative process, then this function will return, this integral will return a zero. So the value of this integral is dependent only on the state of the system and not on the path. Well, anyway, so this was a state function. They found that it was useful, and so they gave it a name. They said it is S, entropy. And it wasn't until later that it was sort of understood that this funny esoteric mathematical notion here actually has some correlation to notions of orderliness and chaos and sort of our more common modern ideas about entropy. We could say that systems with high entropy are disordered. But what we really mean is that there are lots of different configurations that correspond to that state. Okay, so I promise we'll make it kind of clear what this means. I just want to first set it up a little bit. So low S systems are highly ordered, okay, instead of disordered, and there are few configurations. And perhaps the easiest way to think about the orderliness on the molecular level is to think about our different phases of matter. And so a solid is down here at the, I'll write out solid, because S also means entropy. So a solid is down here at the low entropy side. The molecules in a solid are rigidly held in place. They can't move around, and so there aren't any configurations in space, for example. They're all in the same position. You do have some different ways to partition the energy between the molecules. Some of them are vibrating, some of them maybe are in an excited electronic or nuclear state. And so there is still some disorder in a solid system, but not very much, and it's all sort of having to do with energy levels. Well, then we can have a liquid or aqueous. And now, in addition to all the energy levels that a solid would have, we also have molecules that can flow past one another. That's why liquids will flow. And in an aqueous solution, then your solute is also able to flow and move. And so you could have particles that have all the same energy levels, but now they're able to swap positions. They're able to move on top and below and around and past one another. And that creates more configurations. There's more disorderliness, and it's higher in entropy. And then finally we'll have the gas phase, the highest entropy phase. And not only are the gas particles moving past one another, but they're also expanding and occupying as large a volume as they can. And that just gives you more options about where are these gas particles located. A configuration would consider the position of all the different gas particles, and with more volume, more space for them to occupy, of course we're going to have a greater number of possible configurations. Okay, so that means that upward phase changes from a solid to a liquid, or from a solid to aqueous phase, or from a liquid to a gas, that will be a process where the entropy change for the system is positive. And a downward phase change, condensing a gas or freezing a liquid to a solid, will give an entropy change for the system, which is negative. Let's talk about some other ways. Well, I'll leave this up here. Okay. So there are some other factors to consider. So one of them is the phase of the products versus the reactants. Another one would be the volume. So if your process isn't necessarily a chemical reaction, but just like maybe expanding the volume of a piston, or popping a balloon and allowing a gas to expand to fill the volume of the room, higher volume is higher entropy, and lower volume is lower entropy. You can put a couple more here. Lower temperatures have lower entropy, and higher temperatures have higher entropy. So if I take something and I cool it down, then that process will have a negative delta S for the system. It will be losing entropy. If you cool it down enough, then the molecules will stop moving, they'll stop vibrating, they'll stop existing in excited electronic states, and your number of configurations will begin to drop, and so your entropy drops. And then one more. There is one more. Yeah, there we go. I almost forgot the last one. Just the number of particles. So you can have reactions that will change the total number of particles. So if I have a reaction that starts with 2 moles of gaseous reactants and ends up with 8 moles of gaseous products, well, even if they occupy the same volume and have the same temperature and they're all gases, the fact that the reaction produces 8 moles of product for every 2 moles of reactant means that we'll have increased the entropy of the system. And we can say the reverse. If you go from many moles to few moles, that will tend to decrease the entropy of the system, all else being equal. Of course, if I have 8 moles of solid going to 1 mole of gas, well, then that 1 mole of gas, by virtue of being a gas, might have higher entropy than the 8 moles of solid. So every one of these is kind of independent, and we'll give you examples to compare where you only have to think about one of them at a time. One other. Oh goodness, I did forget one in the end. Okay. So there we are. So if you have things that are separated versus things that are mixed. So if I have 1 beaker of ethanol and 1 beaker of water, then together, collectively, they'll have a certain amount of entropy. But if I just pour them into one another and allow them to mix, well, now they'll have a higher entropy. And you can think of it as like, well, now they both collectively occupy the summative volume of both of them. And so this can kind of be thought of as a factor of volume, at least when you're considering liquids. But for gases and for solids, the volume might not change upon mixing, and still even then, mixing things together is going to be more disordered than having them separated out into the pure substances. Okay, I'm pretty sure I did not miss anything there. Okay, so in the end, the entropy of the entire universe is going to be greater than or equal to 0. I've just described a bunch of processes where the change in entropy for the system could be negative, could be less than 0. So in section 3, I believe it is, we'll kind of explore how the second law of thermodynamics is preserved in that case. We'll come back to it. Okay, and now we enter Boltzmann. Boltzmann. Boltzmann was an incredibly clever fellow, and he realized this. It was this grand intuitive leap to realize that entropy, what up until then people have been thinking of as the integral of the heat divided by temperature, could actually be related to orderliness on a microscopic scale. He's the one that introduced our more modern conceptualization of entropy. And Boltzmann came up with this formula. S, the entropy, is equal to K times the natural log of W. Now, because there are so many K's, rate constants, equilibrium constants, etc., I like to put capital B there, just to make it clear that I'm talking about Boltzmann's constant. And so this is Boltzmann's constant. Boltzmann's constant. And Boltzmann's constant has a value of 1.38 times 10 to the negative 23rd joules per Kelvin. And this joules per Kelvin, that's the proper unit for entropy, which is a little weird to wrap your head around, but you'll get used to it. And Boltzmann's constant is a very small value. What's really, really mind-blowing is that Boltzmann's constant, it's a lowercase kb, is actually equal to R, the gas constant, divided by Avogadro's number. And so remember, the gas constant has many different forms. One of them is 8.314 joules per mole Kelvin. Well, if you divide that by Avogadro's number, that will get rid of the mole, and you'll just have joules per Kelvin, and it'll actually equal Boltzmann's constant. And so R is like the Boltzmann's constant for a mole, and Boltzmann's constant is the Boltzmann's constant for a single particle, which is pretty interesting. But remember, there's also the other form of R, 0.08206 liters atmospheres per mole Kelvin. That's the R that we use in PV equals nRT to calculate pressures and volumes and temperatures of ideal gases. And I honestly kind of don't get it. Maybe I need to go back and read some original publications by Boltzmann himself. It seems incredible to me that the gas constant that we use in the ideal gas law is actually related to Boltzmann's constant, which is sort of used here to define the entropy of a system based on microscopic microstates. So anyway, maybe you're not as excited about that as I am, but I just think it's really cool. All right, so K, ln is just the natural log, and then what is W? Well, W will get developed more if you move on to Chem 3610, but we'll just call this the number of microstates. Those microstates are sort of similar to the configurations that I was talking about earlier. So let's think about what the value of W will be for different systems. First of all, if we don't need to consider positions, if we're thinking of something like a solid or like an abstract system like rolling dice or choosing cards from a deck, etc., then W will equal X, which is the number of different possible states that a single particle can exist in, raised to the power of N, which is the number of particles in your system. So if I'm going to be rolling dice, for example, if I wanted to know the number of microstates in a particular die roll, then this would be 6 raised to the power of N. If I'm rolling just one dice, then W is 6. If I'm rolling 2 dice, then W is 6 squared, or 36. If I'm rolling 3 dice, then the number of possible individual microstates or rolls of that dice will be 6 raised to the 3rd power. I don't happen to know that off the top of my head, but you see the idea. We can apply this to particles by saying, well, if I have a sample that contains 12,000 atoms, and each atom has an equal probability of being in one of 3 different energy states, then that would be 3 raised to the, what did I say, 6,000. Right? The number of states is the X, and the number of particles is the N. So that's one way to solve for W, and that in particular applies to solids. When their physical location is held rigid. There's another way to think about W for gases. And actually, oh goodness, I need to not go down the rabbit hole here too much. For what I'm about to tell you about for gases has to do with their positions in a container. And really, a gas can have both energetic states and positional states, and so W really ought to be the product of the two of them. Okay, I'm not going to go down that rabbit hole. Oops, wrong one. Okay, so here we have figure 18.2. Actually, let's just go back real quick. This is the microscopic view of solids, liquids, and gases, and hopefully you can see how, of course, the amount of disorder or the number of different possible configurations increases as we go from a solid to a liquid, and then increases yet again as we go from a liquid to a gas. Here we can see a gas that's confined to 1/2 of a chamber. If we remove the divider, we all know what's going to happen. The gas will rush over to the other side to fill that vacuum, and now the gas has access to a larger volume, and so this is a positive delta S process. And now let's look at different microstates for system which has 2 gas particles. Here they're labeled A and B, and those particles are in a chamber that has 4 sides to it, and so they could be both in the upper left corner, both in the lower left corner, both in the upper right corner, both in the lower right corner, or they can be partitioned in sort of these different ways. Each of these different configurations is called a microstate. And so you can see there's a total of 16 microstates. If we wanted to find the entropy of this system, then we would take Boltzmann's constant times the natural log of 16. In fact, let's go ahead and do that. Why not? Give me a second, let me pull up my calculator. Oops, it's grabbing the wrong thing. I can fix that. You're going to see what that's all about later. Okay, there we go. I have Boltzmann's constant programmed in here already. So I'll take KB times the natural log. Actually, I think I've got the natural log programmed in as well. Times the natural log of 16. And there we have it. 3.83 times 10 to the negative 23rd joules per Kelvin. That is the entropy of our system here with 16 possible different arrangements. Now, I don't want to get too far into this, but I do want to briefly mention that there is a difference between microstates and macrostates. And so if you look at these first two configurations up here, there are two different configurations here that would share identical physical properties. For example, they would have equal pressures on the left side and zero pressure on the right side in this highly idealized, highly simplified system. And similarly, we've got two different microstates where they're on the right two. Here we've got two microstates where they're on the top two, bottom two, upper left, lower right corners, and lower left, upper right corners. So those are examples of different macrostates. This is also a macro state where they're both in the upper left corner, but it has only one microstate. And so we're half as likely to observe the particles in this macro state as we are in that macro state. All right, all of this is very kind of abstract in a way that's hard to understand, and so I did my best to try to write a program which is going to maybe help explore some of these ideas a little bit more. So this is an ideal gas simulator where each of these particles is moving around and they bounce off one another, and it's kind of like what it would look like if you had an actual ideal gas. And if I randomize the positions, you'll notice that each of these different positions where I've randomized all the particles' positions, and you'll notice that they are all unique. Every time I push the button and they go crazy and move around, they are going to be in a unique microstate. However, the basic properties that we would expect the gas to be exhibiting in terms of temperature and pressure and volume are the same for all of these, or at least for virtually all of them. The gas particles seem to be pretty evenly distributed. We've got collisions occurring with the top, bottom, left, and right walls at more or less a uniform frequency. And this is where statistics becomes really powerful in using thermodynamics to make predictions about macroscopically observable variables of the system. And so what we would say is that a more or less even distribution of gas particles is the macro state that we are most likely to observe. Now here I've got a particular microstate, and what I'm doing is swapping the positions around, and so you see there are a number of different microstates where you have all of the particles bunched up in the upper left corner. It looks like an American flag or something. And there are a number of different microstates, but hopefully you can appreciate that compared to all of these different microstates, now it looks like I'm going warp speed, this macro state where all of the particles are bunched up in the corner is very unlikely. because the number of microstates here is much smaller than the number of microstates there. And if I start in a macro state where they're bunched together and just let them go, you'll see that the system does naturally evolve into that most probable macro state. And that's just a matter of statistics. As the particles are moving around randomly, they're given random initial velocities, and they're going to end up as a evenly distributed bunch of gas particles before too long. Now here, I'm going to start them going, and they're obeying the same laws as before. That is, they're colliding in the same ways, there are no forces acting on them, and yet you see them all coalescing up into the upper left corner. Hopefully you have some bit of an intuition that gas particles don't actually do that. But the reality is there's no reason they couldn't do that. It doesn't violate any natural laws for them to do that. It's just that it's extremely unlikely. And so while this configuration looks like a random configuration, it looks like it belongs with all these others, this configuration here, the one which will eventually evolve into having all the particles in one corner, that was very, very carefully chosen. I actually started them in the corner and I ran them for 30 seconds, and then I grabbed their positions and velocities and I just reversed their velocities and called that my new starting position. So I am able to essentially run the clock backward and see them all coalescing back together. And so it looks very unnatural. In fact, it probably looks intuitively to your mind like a video being run in reverse. And that's because we tend to see systems that move from low entropy states to high entropy states, like we're seeing now, instead of seeing high entropy states evolving into low entropy states like we're seeing now. Anyway, I think this program is kind of a fun demonstration, but we're going to pretty quickly move on. What I really want you to know and remember from this section is how to make simple comparisons between the reactants and products of a process and predict whether delta S is positive or negative. Does it involve a phase change? Does it involve a change in the number of moles? Does it involve a change in volume or temperature? That sort of thing. And applying Boltzmann's definition of entropy, taking the Boltzmann's constant times the natural log of the number of microstates. And we'll explore both of those in our first quiz.